Good afternoon, everyone. I'm Zhengxiong from Tsinghua University. I'm going to introduce our work about protocol fuzzing. This shows a basic flow of the protocol fuzzer. It takes human inputs and continuously generates packets to take the server. Meanwhile, it gets feedback from the server to guide the optimization. For the first part, input and generator, there are two main methods. The first one is mutation-based. This fuzzer generates new inputs by mutating existing ones from a corpus. Without a protocol specification, those fuzzers usually reach a limit. For the syntax, since the protocol packets are highly structured, blind mutation tends to generate malformed packets that are discarded by the program. For the semantics, they have difficulty handling complex parameter dependencies between packets in a sequence. In addition, some protocols, such as TLS, use random nonsense to avoid replay attacks. In such cases, inputs from previous exploration cannot reproduce the behaviors they once did. This makes generation attempts using these attempts ineffective. The second class is generation-based. The fuzzers generate packets based on user-defined protocol model, including date and state model. The state model is given in a graph. It specifies the valid packet sequence when interacting with the server. Here we show an example state machine and its corresponding state model. The data model defines the format of accepted messages. Here we show an example format and its corresponding data model. The protocol often features a massive state space, making it expensive to construct a complete model. As a result, the proto model given by the user often encompasses just a subset of the entire logic. Unfortunately, the generation-based fuzzer strictly adheres to the actions outlined in the proto model, without updating the state model in real time. Therefore, the new behaviors beyond the fixed model cannot be recognized for further exploration. Traditional protocol fuzzers mainly can act as clients to take the server. In this context, effective fuzzing requires expert knowledge. However, the highly complex protocol logic makes this challenge. For the second part, feedback, code coverage is a widely used mechanism to record the execution trace of each input. Besides, some work introduce program state based on the value of state variables in the program. However, those methods require source code or binaries and don't apply to black box fuzzing. We demand a scalable feedback mechanism. To address the challenges above, we developed a black box protocol fuzzer named Bleem. The insight is that the protocol is a bipartite system. This means rather than implementing a client logic from scratch, like existing methods, we can utilize the protocol logic already embedded in existing protocol parties. This is the overview of Bleem. It has two main components, the feedback collector and the guided fuzzing module. Next, we dive into the details of the design. First, we introduce a non-invasive feedback mechanism. We analyze the system output. The insight is that the output packet sequence reveals the inner protocol state. However, direct use of the concrete packet can cause confusion. Using this TLS server hello packets as an example, the version and length field don't closely related to the states, and the possible values can be vast. We abstract away those details and focus only on key fields that determine the packet type, because those fields often return to enumeration fields, like the content type and handshake type in this packet. This method allows us to abstract all packets in a conversation. Each abstract packet only indicates the temporal state of one product party. To model the full state of the bipartite protocol system, we incorporate bidirectional communication information. For instance, the state Q2 in the figure means that the server responds with packet B after the client sends a packet A. We identify the state of each output input and connect the states to form a state trace. Second, we introduce mutation operators on two levels, including the packet and sequence levels. For the packet level, we use structure-aware mutation. For the packet selected for mutation, we first parse it, and then we randomly select several files and perform mutation according to its type. Finally, we rebuild it and form the mutated packet. For the sequence level, we develop packet duplication and disordering. This helps in identifying bugs under network environments with packet delays or losses. Based on the concepts above, we introduce system state tracking graph. This graph tracks the explored state space by continuously merging the state trace. Meanwhile, we label the triggering condition of each transition. Instead of using the concrete packet as existing methods, Bleem records how to generate those packets using the corresponding abstract packet and the mutation operator. The system state tracking graph helps us to recognize the observed state space, and it guides our fuzzing direction. First, we try to stress each state with diverse inputs using the proposed mutation operators. Consider the SSTG as the rise. If we choose the state Q2 to test, we first enter the state Q2 using the abstract packet sequence A plus sigma 0. Then we use a new pattern, B plus sigma P, as input for Q2. As a result, we can trigger a new state trace as shown in the background. For a second strategy, our goal is a comprehensive SSTG traversal by targeting low-density areas. This is accomplished by a pause schedule, where transitions with fewer execution times are given higher selection priority. It's worth noting that the packets on the transition label are given at an abstract level. As a necessary step, we instantiate those packets before mutation. To ensure logic correctness, we leverage packets intercepted during real-time interactions between the client and the server. For the evaluation, we compare Bleem against 5 fuzzers. First, we use branch coverage as a uniform metric to measure the fuzzing effectiveness. The results show that Bleem achieves higher branch coverage than existing product fuzzers. For the guided sequence generation, we implement Bleem run that use random sequence selection for comparison and come to 3 conclusions. First, Bleem achieves more complex SSTG and more branches than Bleem run. Second, the graph complexity correlates positively to the coverage, indicating that the graph can reflect the inner execution in some degree. Third, the total number of state traces is finite, indicating that our design prevents state space explosion. For the bug detection, Bleem discovered 15 new bugs. Only 9 of them can be exposed by existing toys. On closed source targets, Bleem also achieved the best CVE discovery performance than existing product fuzzers. In summary, Bleem provides a scalable feedback mechanism and supports guided fuzzing. It also leverages interactive traffic to generate protocol logic of well-packed sequence. So that's all I have, and please read the paper for more details. Thanks for listening, and I'll take questions.